Hi, everyone. Welcome to my presentation. My name is Elmachtoub, and I'm a professor at Columbia IOR and the Data Science Institute. This is joint work with Omar Besbes, my colleague at Columbia DRO, and my former PhD student Yunjie, who is at TripAdvisor. The title of our work is Static Pricing, Universal Guarantees for Reusable Resources. So what is a reusable resource? Basically, it's a resource where when a customer is done using the unit, another future customer can come and use that same unit. Common examples are hotel rooms, airline seats, ride-sharing vehicles like Zip cars or Uber cars, and cloud computing servers. In all of these settings, when a customer is done with their service, another customer can come and use a unit of inventory. The reusable resource that actually motivated this work is born out of a project with an industrial partner. We won't present all the details here, but they can be found in another paper. We worked with a large aircraft OEM, original equipment manufacturer, that makes airplanes or aircrafts. And these aircrafts have very expensive rotable spare parts on them, which are a type of reusable resource. When a rotable spare part breaks, you don't throw it out. You actually do what's called an exchange sale, where you take the rotable spare part and you give it to the manufacturer. The manufacturer gives you a working part. Meanwhile, the manufacturer will take a few months to repair that part and put it back into their inventory to be sold. Here's an example of a warehouse of reusable resources, and here's a specific one called the thrust reverser. So some of the challenges that our industrial partner faced were around finding the optimal prices for these rotable spare parts. In particular, each part had different inventory dynamics because they had different units of inventory, demand, repair times, prices, and costs. For many of the parts, there's also a lot of competitors. So they were losing out on market share due to competitor prices. And generally, the amount of data here is very limited because each part is designed to last a very long time. There's competition, and the number of aircraft is relatively small to begin with, a few thousand. So estimating parameters here is very challenging, especially a demand model because prices rarely change. But our goal was to develop a dynamic pricing solution for them that captures the inventory dynamics of rotable spare parts and aims to maximize profit without impacting too much the service level and market share of the rotable spare parts. So service level is the probability that we have at least one unit in stock, and market share is the probability that the customer buys from the manufacturer. So before going to the results, I'd actually first like to show you the model that we implemented and then describe our theoretical findings. So what's the model we actually implemented with our partner? So this model was applied to all of the 2,000 roughly rotable spare parts. So this model was calibrated and implemented 2,000 times, once for each spare part. So C is the total number of units for each part. Mu is the repair rate, and 1 over mu is the average repair time. And we assume the repair time is exponentially distributed. Little c is the average repair cost. Lambda p is the arrival rate or demand rate, which is a Poisson process and is modulated by the price p. Capital lambda is the overall market size, and f bar of p is simply the probability that someone buys at price p. It's useful to think about the inverse of lambda p, which is p of lambda. So the reason why we think about this is because it makes our analysis tractable, and we're going to assume that lambda times p of lambda is concave, which is just the standard regularity assumption in the revenue management literature. So our decision variables are lambda I, which is equivalent to choosing the price pi. So lambda I is the arrival rate we want when there are I units in stock. So above, you can see that our system actually is just a simple Markov chain where there are C+1 states. So 0 means we have 0 units in inventory, and we move to a state with 1 unit inventory at a rate of C times mu, because there are C units in repair. And we move from 1 to 0 at a rate of lambda 1, which connects to the price P1 when there's 1 unit of inventory. Similarly, at the state 2, we move to the state 3 at a rate of C minus 2 times mu, because there are C minus 2 units in the system that are being repaired. And we go from 3 to 2 at a rate of lambda 3. This is also known as an Erlang loss model. It's important to note that when a customer arrives and this state is 0, that customer is lost. So that's a lost sales. And the reason for this in practice is that because customers cannot wait to get a spare part because it is very costly to keep their airplane grounded. So the objective is to choose these decision variables, lambda 1, lambda 2, lambda c, which will correspond to the prices changing dynamically as the inventory changes. And we choose these variables to maximize some combination of profit, service level, and market share. So just to give you a sense about the data, so it's important to observe that the value for C, the number of units, or pool size, as they call it, is very often less than 5. And the most common choice of C, or in the data, is C equals to 2. So for most of the roadable spare parts, they only have 2 units, which are repaired and resold over and over again. On the right, we're plotting the coefficient of the inter-arrival time and the repair time. So coefficient of variation should be 1 for an exponential random variable. And here we plot the coefficient of variation for all the roadable spare parts. And you can see that the distribution is obviously varying from 0.5 to 2, but hovers nearly around 1. And most importantly, it's clearly very far away from 0, implying that indeed the inter-arrival times and the repair times are random. And since these are relatively close to 1, an exponential distribution seems to be an appropriate assumption. So let's summarize the model with a little illustration here. So C equals 6 in our model. We have currently 4 units in the warehouse and 2 in the repair facility. So the arrival rate is currently lambda 4. First customer comes, we do the exchange sale. We send the broken unit to the repair facility. We incur a repair cost, C. Next unit comes. We do the exchange sale. We send the broken part to the repair facility. And now C equals, the number of units that are available is equal to 2. So we have the current rate is lambda 2. Eventually, one of these units gets done repairing and it comes back to the warehouse. So now the arrival rate is lambda 3. So after we built this model and it was verified with data, we did a simple test to see how well does the optimal static price do versus the optimal dynamic pricing do, so we can understand the potential benefit of dynamic pricing. And we did this for different values of C, different demand models, linear, exponential, logistic, and many ranges of parameters. And in this table, we report the worst case. And to our surprise, we found that static pricing policies are always within 2.5% of the optimal dynamic price policy. In fact, this means that the ratio in this table was always 97.5% or higher. And these are worst case results. So the immediate consequence in terms of practice is that we focused, rather than us focusing on dynamic pricing, we focused on finding the best static pricing policy. And more on that can be found in our other paper. But this prompted a theoretical question. Can we actually prove that static pricing is universally near optimal in this model? And that's what we'll talk about for the rest of the talk. Why is it important to show a universal guarantee? Well, first of all, dynamic pricing policies can be difficult to compute and implement in practice. In our model, it is tractable to find a dynamic policy, but simple static policies are definitely preferred. We also see that numerically, it only adds 2.5% in value, and that's in the worst case. Often it's within 0.1%. And since the estimation of the parameters is so difficult, especially in the small data environment, it's hard to justify implementing dynamic pricing when the parameters themselves are noisy. In addition, it's very hard to do dynamic pricing if you don't have a reliable demand model. And in our case, the prices change so infrequently, it's hard to compute a good demand model. Finally, from a theoretical angle, static pricing is known to work asymptotically well in large systems, But in our application, the number of units was often very small, less than 5. So I will skip most of the literature review, but there has been a lot of work on reusable resources, particularly when the number of units is large. People have shown that the convergence rate is on the order of 1/c. Okay, so let me explain how we'll analyze this problem. So we're going to look at the steady state probabilities. So PI is the steady state probability of having I units of inventory, and it's going to depend on the policy pi. So pi is just the set of arrival rates, lambda 1 through lambda c. And using these steady state probabilities, we can characterize the profit, the market share, and the service level using these steady state probabilities. So service level is just 1 minus the probability of having 0 units in stock. And what is the static policy we're going to use? So for the proof of our result, we're actually going to rely on constructing a static policy that comes from the optimal dynamic policy. This is fundamentally different than most of the literature that uses a fluid optimal policy. Here we use the true optimal policy denoted by lambda I star, and pi star is the optimal steady state probabilities. So the static pricing policy we're going to analyze, lambda tilde, is computed by taking essentially the average arrival rate in the optimal system when you have at least 1 unit in stock. Again, the static price policy set that. So the arrival rate in the static system is the same as the arrival rate in the dynamic system, conditional on having at least 1 unit in stock. In practice, of course, you can just find the optimal static policy. For the proof, we will use this constructed static policy, lambda tilde. So what is the theorem we can show? Basically, we show that the static policy lambda tilde simultaneously guarantees 15/19 of the profit, market share, and service level of the optimal dynamic policy. And this holds for any set of parameters. So any arrival rate, any demand rate, as long as you have the regularity, any combination of the objectives, any choice of C. So even when C is small. Okay, so we guarantee 78.9% of all 3 objectives simultaneously. Okay, so this is a rather high guarantee compared to standard guarantees in the literature. It's the first universal guarantee for static pricing with reusable resources, handles multiple objectives simultaneously, and we also can show that the analysis is tight, meaning that we have an example that achieves 15/19. The proof works in 3 steps. First, we show that we can bound the ratio that we're interested in of the revenues of the 2 policies by the ratio of the stock-in probabilities. So the top is the stock-in probability of the static policy. The bottom is the stock-in probability of the dynamic policy. Then we can show that this ratio is equal to this very complex polynomial. And in fact, within this polynomial, we do a change of variables. So we go from this lambda space, lambda stars, and we do a substitution to this z space. And then we show that this ratio can actually be analyzed using a lot of calculus and algebra. So when c equals 2, you can directly write down this ratio, and you can see that the ratio is at least 4/5. When c equals 3, you can see the ratio is 15/19. And then using lots of calculus and algebra, we can prove that c equals 3 is the worst case, which I won't explain here. But this is just 1 page of our paper. It's a lot of algebra. And each step is relatively straightforward, although there's a lot of such steps. Now, we can also show that we can get close to this 97.5% in the most common case we saw in practice, when c equals 2. So if c equals 2, and we assume the demand is linear, we can actually prove that static pricing guarantees 95.5% of the optimal solution. And now this result uses the same ideas from the previous one, but we also use some of the optimality conditions on the profit rate to tighten the range of the worst case values. And we take advantage of the fact that the linear demand model always has the same derivative regardless of the arrival rate. So to summarize, We provide the first universal guarantees that static pricing is universally near optimal. And our analysis relies on new ideas that leverage the optimal dynamic policy, not the fluid relaxation. Practically speaking, static pricing is more than sufficient, especially when the number of units is small. And this was against our regional intuition and might have large implications for practice. And finally, I just want to say thank you. Feel free to email me if you have any questions. And here are the 2 papers that I referenced. Thank you for your time.